Okay, let's talk a little bit now about the properties of Markov chains. Okay, so Markov chains are going to behave a little bit differently than the state diagrams that we've seen before. And this is because of that dominant eigenvalue being 1. So what we're going to see is that um, because the dominant eigenvalue is 1 and the total amount isn't changing, they're going to converge to what's called a steady state. Okay, so a steady state eventually our model will converge to a fixed vector of values, right? And so we'll end up with the same, we'll end up with, depending on our model, possibly depending on the initial state, we'll end up with the same result at the end, regardless of kind of how we go. We're gonna converge to something fixed. Okay, so if you've got a matrix like this, you can actually figure out what this will converge to using eigenvalue analysis, just like we did in with regular state diagrams. Okay, so if you look at this matrix, you can compute the eigenvalues and the eigenvectors. So this is the same one from the Markov chain that I had up on the previous video. So if you've got that one down, this is the exact same one. If you look at the dominant eigenvalue, as I said, so the dominant eigenvalue is 1, okay? And the eigenvector associated with that, if you want to pause this video and go run it through Wolfram Alpha, you can see that the eigenvector that you get in Wolfram Alpha is 1.70, 2.43, 1. Okay? And so remember, Wolfram Alpha always does this thing where it makes the final value of the eigenvector 1. And we like to think of these as percentages instead. So what we're going to do is we're going to add all of these up. Right, so 1.7 plus 2.43 plus 1, divide out to get an eigenvector that's percentages, right? So 1.7 plus 2.43 plus 1 gives us, what's that, 5.13. 5.13. If you go ahead and divide out by that, you're going to get an eigenvector 0.33, 0.47, 0.19. Okay? And so if you run a simulation, and say you start with 40% in state 1, 50% in state 2, 10% in state 3, right? So if you start with anything, so say you start with 40% in state 1, 50% in state 2, and 10% in state 3, right? We think of these as percentages, so these add up to 1. You're going to end up with 33% in state 1, 47% in state 2, and 19% in state 3. If you started with other percentages, you'd end up with the exact same thing, okay? And so I'll post a simulation on Blackboard with these lectures in Excel, and you can see exactly this happens, okay? So that's what happens with a Markov chain like this. There are going to be more interesting Markov chains, though, where the eigenvalue, the dominant eigenvalue, isn't unique. Okay? So remember when I said in class that all of the eigenvalues are different, everything behaves very well? With Markov chains, you can sometimes get into a situation where there are two eigenvalues that are both equal to 1, and they both dominate. Okay? So we'll talk about that situation. I want to talk about a tool that we're going to use to look at those kinds of situations first, though, and that's what's called the steady state matrix. Okay? So if you remember, so let me just write up my dominant eigenvalue here. So remember the dominant eigenvalue was 0.33, 0.47, 0.19. Okay? So the tool that we're going to use to look at Markov chains is what's called the steady state matrix. And what this is just the limit as n goes to infinity of this particular matrix A to the nth power. Okay, so remember when we talked about state diagrams, we talked about how the fact that x sub n is a to the n times whatever our initial value was, right? And so what happens with Markov chains, because this actually converges, right? This matrix converges to something fixed. This limit actually exists. It doesn't just keep increasing because it is some sort of steady state. So this actually can be computed, okay? Now, of course, taking this limit, right, if you think about how complicated matrix multiplication is, taking this limit could be really hard. What we're going to do in practice is just say that this is roughly the same as a to the 100 or something like that. And that's something Wolfram Alpha can do to you, for you. You can take a matrix and just raise it to a power. And so if you look at this matrix a to the 100, for this particular matrix A, it comes out to 0.33, 0.33, 0.33, 0.47, 0.47, 0.47, 0.19, 0.19, 0.19. So this steady state matrix is just 3 copies of our dominant eigenvector. So this is another way to see the dominant eigenvector coming out of the problem. Okay? So what that tells us is that, and I'm going to put a little star here, in many cases, put a little star because this isn't going to be true in all cases, and we'll talk about the ones where it's not. The steady state matrix gives the percentage in each category after it reaches a steady state. So if you ran this model long enough, you would end up with 33% in x1, 47% in x2, and 19% in x3. Okay? So that's in most cases. We're going to talk about the interesting case, which is what's called an absorbing Markov chain, next.